I'm very happy to introduce some of our recent work from, so mapping the Methane point source emission from the Chinese satellite, hyperspectral satellite. Also, we also using some other satellite. Last year or even this year, tried to work with last year work with Evan and Saha for the Stanford campaign. So this year, I think they're still working on the field campaign from at the Wyoming and also the Arizona side. So it's ongoing at the moment. So just a very quick background. I think everybody knew this. So we knew the methane, the very second largest contributor to the greenhouse gas, globally. So it has a high global warming potential. So and short lifespan. So it contributes about 20, one fourth of the global warming. So in COP 26, so the signing of the global methane pledge. So right now there are more than 150 countries, which signed this pledge. So this signifies the methane emission reduction, have attracted global attention from, government and even the some enterprise. The things, so, globally and regionally, the energy part sector, including oil and gas and other common, and also to contribute a large fraction of the methane emissions. So given the methane's higher global warming potential, so targeted measures in the energy sector can significantly impact overall greenhouse gas emissions and their climate effects. So most important is the emissions in the energy sector, is very immediate and significant. So implementing any effective strategies and technologies to detect or reduce the methane leaks from like oil, gas, and common emissions can lead to substantial reductions in a very relative short period. And also, these emission reductions, are not only climate benefits, can also have significant environmental and economic advantages. So, economically, we capture this methane lost, from also the like oil fly venting or something. So can create additional revenue streams for the energy companies. I remember even just published the paper in Nature a few weeks ago. So I think this lost quite a lot of money. For our two countries, so China and the United States are also the two big countries with the highest global anthropogenic basin emissions. So the energy part sector is the largest contributor for these two, for both countries. So, for the US, the oil and gas, the production, the main source of emissions within the energy part. So in 2019, the US oil gas industry emitted more than, I think, 8 million kilograms 8 teragrams of methane. So it's almost 1/3 of the national total emission from the anthropogenic source. For China, so the methane emissions from coal is the largest contribution. So in 2019, it's around more than 21 teragrams. So from the whole country. So it's more than 30% of the total emissions from for the country. So this highlights the very urgent need for China, to adopt more sustainable mining practices to mitigate the emission, footprint. However, there are still significant uncertainties in the estimation of the methane emission from the, this is just one example for the coal mine in Shanxi province. This is the largest coal mine area in China. So you see on the left, so the result for the Shanxi, the inventory, this is from the bottom-up inventory. So it's quite a big difference from 4 to 7 8 teragrams. This almost twice different. So there's a very urgent need for high-resolution methane estimation technology that we can assess the methane emissions at the local, regional, or even the country scale. So current methods often produce a inconsistent result as shown here on the left or even on the right from different for different provinces in China. So the high resolution estimate technology could enable more precise identification of the missing source and their temporal trends across different scales. Also, we could help pinpoint specific emission hotspots, some some facilities. For remote sensing, especially satellite observations are very important approach to detect emission from global, regional to local scales. So many countries like the US and the European and China are deeply engaged in the field of emission monitoring using the satellite or remote sensing technology. These efforts involve deploying advanced satellite platforms and also the airborne sensor to detect and quantify emission accurately. So at a global scale, we have the GOSAT and GOSAT GW from Japan. So they can provide global coverage of the monitoring emission concentrations in the atmosphere. Then this enable us the identification of large-scale emission patterns and trends. At the regional scale, right now, the European, the Aisa Sentinel-5P Troponin satellite, and even the recently launched mission site from the EDF in the US can assess emission at the relatively high resolution for the regional scale. So these help us quantify emissions from specific regions, such as oil and gas production. Importantly, there is in the last 5 years, the advancement in the very high resolution satellite can help us to detect the point source emissions. So allow us for detection quantification emissions from the individual facilities. These instruments, in particular, the high resolution hyperspectral sensing offers a very unique possibility to monitor point source emission. So these instruments cover the emission offsetting band generally around 2.3 micrometers. So allow for better attribution to source, but have a little bit lower detection limits, typically for the emission greater than the 300 kilometers per hour. There are two main classes of the emissions. Like first one is hyperspectral remote sensing, like our Chinese government 5, the German EnMAP and Italy PRISMA, and the US EnMAP. They have around 30 meter per resolution with medium sensitivity. When also the reveal time, so they have a very narrow swath, generally 30 to 60 kilometers. So the reveal time is, sometimes almost 2 months. Then another for the multi-spectral mission like Sentinel-2, Landsat 8 and 9, also in China we have the VMI. So it's quite similar. They have the shorter wave bands in here. I don't have okay. I can use the mouse here. So in this strong oxygen band around 2.3 millimeters. So they have a spatial resolution 20 to 30 meter, but with much lower sensitivity. But they have a very frequent global coverage. So for us, for China, so we have right now, so in space, there are 4 hyperspectral sensors, the Kalman-5 2, Kalman-5 1A. So, and the Kalman-5 1 that was launched in 2019, it lost right now. So we have 2 Kalman-5, also have another 2 satellites, Ziyuan 1, we call 2D or 2E. These 4 satellite sensors are from the same, institute. So they have, very same, characters. So for the Kalman-5, like in the shorter ranges here, they have a 10 nanometers spectral resolution, 30 meters spatial resolution, and 60 kilometer swath. For the Ziyuan series, 02D, 02E, the spatial resolution and swath are the same. The only difference is the spectral resolution. So the beam on in the side on platforms. So in the sphere range is the spectral resolution is 20 nanometers. This is the only difference. So it means the Ziyuan series have a little bit better signal ratio. Next, I would like to introduce. I think most people here are very familiar with the retrieval algorithm. I won't go to it very in detail. So the overall technical framework for Methane, point source Methane mapping algorithm is generally involves 4 steps. So the first one, so is the Methane retrieval. So this step involved the remote sensing data. So then with the data-driven method like the matched filter technology to retrieve Methane column enhancement related to the background from the remote sensing data. The second one is we try to mask the plumes. So generally, before we use the visual spectrum, right now we can use some deep learning models like CNN to mask the plume. Next one, after we got the plumes, we can use the integrated enhancement method to estimate the emission flux rate. So the last one is the validation. We can use some, the end-to-end simulations. Also, if we can use some ground truth, that would be very better. So like even you guys did in the last several years for the control release experiment. However, there's still for the current Methane retrieval algorithm include in the strong like offset bands in the match field, also with the weaker offset bands. These algorithms face issues with low retrieval accuracy, and sometimes maybe we missed detection of some lower emission plumes. So the first issue is the low accuracy. So this just the sensitivity analysis with the end-to-end simulations. You see the slope here. So maybe sometimes we can underestimate the emission rates. So this issue maybe we related to some like atmospheric intervariance, surface reflectance variations, like in some very heterogeneous landscapes. Also, the instrument noise can contribute to retrieval errors. The second issue is sometimes we so use a single opposition window leads to a missed detection plumes. This is one example for the PRISMA for the Stanford campaign in Arizona 2020. So with the strong oxygen bands in this where, so we missed these plumes because this plume probably the emission rate is a little bit lower. We have with these hyperspectral instruments, we have the full sphere range from 1,000 to 2,400 nanometers. So have a strong oxygen band, have weak oxygen bands. So if we can use the full sphere range or sphere bands, maybe you can reduce the uncertainty in the Methane column enhancement retrieval. So here we try to propose an optimized retrieval algorithm that uses a common filter. Here, so we are using the weaker oxygen band and strong oxygen band together. So use a series measurement, the observation of time and continue static noise and other increases to produce estimates of unknown variables. Here we can, with this we can maybe we can accurately make the retrieval. Here is the overall the framework. So there's generally 5 steps. So we have the data, satellite data, then we are using the weak oxygen band, strong oxygen band. Also, we can use the full sphere range bands. So here we initial the mean and the covariance. First type we use this data for the common filter. Next, we are using perform a linear combination of the retrieval Methane enhancement values from these 3 bands. So this type involves calculating the different 3 parameters for the error for the weak oxygen band, the error for the strong oxygen band, the error for the full sphere range bands. After that, so we use the common filter, these errors as input for the common filter to calculate the final emission concentrations. Then this is the iteration process. We can update the mean and covariances. In the end, we can, probably optimize the Methane retrieval result. So for the first, we have to evaluate the performance of the proposed method. The first, we conduct a sensitivity analysis based on the end-to-end simulations. So the red one is our method. So you see in the plot, the slope is very close to 1-to-1 line. So this one, the second column is generally the match field with a strong oxygen band. The slope is also close to 1-to-1 line, but it says the slope here is 0.7. The slope for ours is 0.9. Well, however, this is just the sensitivity analysis with the end-to-end simulation. So if we have the ground truth, that we better to validate this, check the problem of this method. So I think I don't want to show too much. This is I got the slide from Saha last 2 years ago. See the event, you guys did a very good campaign here from October 10th, 2020 to November 30th. We, the NGO team in the, in this campaign, we are, there are a lot of teams, from Stanford, from Valencia, from Keros, from GHGSat. So the NGO team is one of the lucky team to participate. And also we don't need to go to the field. In this campaign, I helped to coordinate several Chinese satellites here, Kalman-5 2 and Ziyuan 102E. Also, there's another one, Hanjin 2B. But eventually, it turns out that this one does work. Have a cause spatial resolution and cause, I think, the signal ratio. For the ongoing campaign this year and next year in from Stanford. So in Wyoming and Arizona, I have requested 4 Chinese satellites. It's Kalman-5 2 and Kalman-5 1A and Ziyuan 102E and 02D. So I think in October 10th, so Kalman-5 has passed the Wyoming side. So next week on September 2nd, the Ziyuan Ziyuan 2E will overpass at the Wyoming side. With this data from this campaign, could evaluate the performance of different retrieval methods, including ours. So the last one, the first column is our method, and the second one is the generally used matched filter method. Except for the PRISMA since on October 27, so I think the very low emission rates. So no method can detect the emission from the satellite. Despite these challenges, our method can also instantly identify plumes across all 5 satellites, Kalman-5, Ziyuan, EnMAP, PRISMA to Permian Basin. So, but for example, for the PRISMA, November 7 and November 13, the match field with a strong oxygen band is looks it cannot detect the emission plumes. But for our method, we can show these plumes very clearly. Next, this maybe is a more direct comparison, for different method. So the bottom right is our method. So you see the regression line with the ground truth. So it's almost close to 1-to-1 line, and with the highest R square and the lowest RMSE, the bears. Also, the retrieval accuracy is a bit more than 13% higher than the matched filter method with the strong oxygen bands. Also, we did a sensitive analysis, for different satellites, try to show the detection limits. So the first row is the Ziyuan, and the second row is PRISMA, and the third row is Kalman-5. So the plot shows the sensitive analysis at different flux rates from 250 kilometers per hour to 2,000 kilometers per hour. You see, looks like the Ziyuan sense instruments has the best detection performance. So even at the lowest with 250 kilos per hour, it can show the plumes very well. For the PRISMA, well, it's that much more noise. For the Kalman-5, see, they only can detect plumes above the 500 kilos per hour. Also, we check the signal ratio for different satellite. So this is along the sphere range from 1 millimeter to 2.4 micrometer. So Goffin 5, like this range, this is the strongest band for Mason. So Goffin 5 display the signal ratio is roughly twice as high as the PRISMA. PRISMA is the brown one. But it's very close to the image, it's the blue, like this part, blue is from image. So the higher, this high signal ratio for Goffin 5 promise means compared to image. So this is higher signal ratio allowed for the improved detection, for missing plumes at this some point source. So next, in the next few slides, I would like to introduce a few examples. So using this satellite to mounting the super missing emitters from oil and gas from Kalman and landfill. So the first example shows some results from North America, mostly in the Permian Basin, during 2020 to actually until now. So we show the data is December of 2013. In totally, over the 2 years, almost 2 years, we identified 139 plumes from 122 facilities. So in Permian Basin, there are more, this is the most part we know. So 131 plumes we identified. These are some examples for the individual plumes from Goffin 5. The on average, so from this 139 plumes, so the average emission rate is around 3,000 kilos per hour. But the emissions show very considerably for different facilities, different plumes, different the lakes. This is one driven very high flux rates, almost 7,000 kilos per hour. This is from a malfunction flare. Well, for this one, the plume Q is from an incomplete compensation of a flare in a well pad. Well, for the plume T and V, this one, so they have a plume around 2,000 kilo per hour. So they are associated with the leakage from a tank battery. We compare with some previous work from like satellite, also with the airborne measurements. Generally, the observed emission intensity in this study, in our last this study, so it's around from 500 to 16,000 kilos per hour. So this is higher than the airborne measurement. Also, you see on the left, the kilometric distributions show this from these 2 years. There's for the higher emission, the right line with the airborne. This is airborne. This is the one from also master. The blue dot is from Achilles work is most of is from Goffin 5. So, but it looks like for last 2020 and 2022 and 2023, so it's much higher emissions. Well, since we have a 2 years measurement, so we also did a system analysis that from January to 2022 to the December of 23rd. Interestingly, in around 2021 or 2020, there's a decline of about 66% after COVID-19. So after that, in spring 23rd and summer of 23rd, so the emission rates increase almost twice. With this measurement, we try to we use the interpolation method for the Permian Basin. So this one, the third one is our estimation for the Permian Basin for these 3 years is around 2.7 terabytes per year from only these point source observations. So this estimation is closely with the Permian inversion, but it's for the 2018 to 2020. So their estimation with the Permian inversion is around 2.2 So, our estimation is quite close to this one. For the facilities, for these 2 years, so the worldwide, so this part is emerges as one for image emitters is around 20%. So for others, the company compressor stations and flaring, so this 12%. Compared to 2019, this is the work from Asia, so it's only for 2019. So it looks like the well bed is much more increased a lot. The second example is the Kalman. So this is for the Shanxi province in China. So we using this satellite, so we try to monitor from 2019 to 2023. So for this several years, we have identified around 260 plumes across 57 Kalman in Shanxi province. This some examples. So emission rate distribution. So this is the Permian Basin. This is the Kalman in Shanxi. It looks like it also showed a heavy tail, distribution. Interestingly, so emission from Shanxi province, from the Kalman, even more high red scaled, so have a higher mean emission rates. With this high resolution satellite, we use we use the interpolation method combined with the inventory. So we estimate the regional missing emissions for the Shanxi province. So our estimation for this several years is almost 9 million tablets per year. So the top right is our estimation. The top left is the Tripoli missing concentration mapping. The two left here is the inventory from GCMT from EDIGA. Then on the last one, the bottom left is the inversion from Tripoli. It looks like the inversion from Tripoli. This is the study from Zhu Chen from the Harvard group. Shows estimation the Kalman from Shanxi quite a lot. Even the inventory here for the EDIGA from different years, 19, 20, 21, 22, they also underestimate the Kalman emission in Shanxi. Most importantly, with this point source measurement from satellite, we can estimate or even can for the very local, very small scales. So here, we use this measurement to map the spatial distribution for 3 suburbs, like county level. So first one is Changzhi, Yangquan, and Luliang district. So our measurement here, like for the Changzhi, this is closely with the ISROM. This is from the ISROM from Tripoli. They have they update the emission for different areas for the Shanxi. So our measurement from this only point source is closely with the ISROM estimates. Also, the second here is our interpolation method. We can get the spatial, very high spatial distribution for these 3 counties. So the top one is the Tripoli concentration map. This one is from EDIGA, this one from the inversion. They have a very coarse resolution. The last example is for landfill. So use this hyperspectral satellite, not only the Chinese one, also with the EnMAP and PRISMA. We found a big missing emission from landfill site in Urumqi, China during 2020 and until now. So totally we found 34 missing plumes in this landfill. So they are very continuous observations for this landfill. These are some examples of the plumes from Goblin 5.1 and Goblin 1B and Goblin 5.2. So the emission rates can up to 6,000 for this, for this one, like March of 2020. It's greater than 6,000 kilos per hour. This is some, here, this is just for all the plumes. emissions. So the highest one, this one almost more than 10,000 kilometers per hour. This one here. This is the seasonal variations for spring, summer, autumn, and winter. The emission is higher in winter. So this is related to the atmospheric pressure reduction. For the summer, is also a little bit higher. So maybe this is we are trying to analyze the the reason for this the difference. So for the summer, maybe related to the high temperature in the summer there. Well, since we have multiple observations over the 2 years, we try to see whether there's a minimum observations to estimate the very robust annual emissions for this landfill site. In 2022, there were 8 satellite overpass in this here. So first we use all the measurement to with the average, and then we upscaled for the annual emission estimation. Then we use a random sampling to see what is the minimum overpass or observations we can require to stabilize the mean within the overall mean within the 30% of the 8. This is for 2023. See, we have more than 20. There were 21 overpass. Generally, we see we need at least around 6 to 7 overpass for this to stabilize. This one. You can see to estimate the annual mean emission for this landfill. Okay. So I think that's what I would like to share today for to map the mission with the Chinese satellite. So next we can take the questions if there are any questions.